Welcome to the second video in a series designed to provide guidance in the process of setting up and running a two-dimensional sediment transport model with SRH2D. In this video, we will discuss recommendations for converting an existing hydraulic model to one that is tailored for sediment modeling. Topics covered in this video include the model extent and considerations for adjusting the mesh, reviewing the upstream and downstream boundary conditions, creating and assigning sediment material zones, and the use of monitor lines and points. When reviewing the model extents, the upstream extent should be sufficiently far from the area of interest to mitigate the effects of introducing sediment at this boundary. The goal is to ensure that uncertainty in the amount of sediment introduced will have minimal effect on the area of interest. The downstream end of the model should be placed in a location that is not expected to aggrade or degrade relative to the rest of the model. Velocity is a good surrogate of transport potential, so if the hydraulic results are available, areas with increasing velocity, like riffle crests, are a good target. Areas where the velocity is decreasing, like pools, may be problematic if excessive aggradation occurs and affects the upstream hydraulics. This example model was initially developed to study the hydraulics at a bridge opening. The model extends about 1,000 feet upstream of the bridge, and the results indicate the hydraulics are well represented. However, at the upstream boundary, velocities are high relative to those immediately downstream. While not consequential for a hydraulic model, for a sediment model, this could result in a very high sediment load calculated at the boundary that is quickly deposited in the area with reduced velocities, which then may result in a change in topography that affects the performance of the model at the bridge, which is the area of interest. This boundary effect can be mitigated by moving the model boundary further upstream. In this case, the model was extended about 1,200 feet further, and hydraulic results indicate less variation in the velocity at the boundary. Moving the boundary upstream also creates a buffer area where uncertainties in the introduced sediment load can balance out with the transport capacity of the rest of the model. Excess sediment can settle out, or additional sediment can be sourced from the channel bed in this upstream area in a way that is less likely to affect the area of interest. The total upstream extent necessary for this adjustment to occur will depend on the channel and topography. In this case, the boundary is approximately 20 channel widths upstream of the area of interest. Once the model is assembled and executed, it will be possible to evaluate if this buffer is sufficient. With the extent boundaries established, the mesh element number and size are two other aspects to evaluate when converting a hydraulic model to a sediment model. SRH2D is robust enough to handle model meshes with up to hundreds of thousands of elements, and there can understandably be a desire to create a fine mesh resolution to ensure that the results are as accurate as possible. However, the instinct to build a large mesh with many small elements must be balanced with the practical usability of the model and the effect on the model results. As most users are likely already aware from hydraulic modeling, SRH2D model runtimes increase as the number of elements increase. What should be remembered as well is that because of the increased computational tasks, sediment models should be expected to take much longer to execute than a comparable hydraulic model. It is not uncommon for a sediment model to take many hours and even days to complete a run. Depending on the application, these long run times may interfere with the ability to develop the model, iterate alternatives, and analyze results in a timely manner. There is also the case of diminishing benefit when using smaller and smaller mesh elements. In some circumstances, coarse elements can produce results that are not meaningfully different from fine elements. It's therefore common to have a balance of large and small elements when developing a sediment model that is ultimately useful. A common scenario is starting with a hydraulic model that has a large total number of fine mesh elements. While SRH does not have a defined maximum number of elements, a total number between 10,000 and 20,000 elements will generally result in reasonable execution times, though some cases may warrant a larger total number. Techniques for reducing the element total include reducing the total model extent area, increasing the size of elements that are away from the area of interest and are not likely to experience significant aggradation or degradation, and using quadrilateral elements instead of triangular elements. For example, this mesh is a close-up from a model of a channel and floodplain that performs well for generating rigid boundary hydraulic results. And this is the same modeled area where the mesh has been updated in anticipation of running sediment calculations. Channel elements were changed from triangles to quadrilaterals, and the size of elements in the floodplain increased in size as you get farther away from the channel. These changes reduced the number of elements by 2/3, with no loss in analytical value of the model. At the same time, it may also be necessary to increase the resolution of elements within the area of interest. Convention for hydraulic modeling is to use about 10 elements across the width of a channel. For sediment modeling, it may be appropriate to increase the number to 15 or 20 or more elements if the analysis focuses on one point in the system. A recommended approach is to evaluate the effect that decreasing element size has on the results. The upstream boundary of the model extent defines the location of the upstream boundary condition. In defining the upstream boundary condition, the modeler prescribes the width of the boundary arc and determines how flow and sediment enter the model domain. Care should be taken to make sure the boundary arc width and distribution of flow matches the natural condition of flow in the channel and floodplain. The image on the right displays the velocity profile results of a model for an approximately bankfull flow where the upstream boundary condition extent is limited to the channel. For this model, the area of interest is the downstream bridge crossing. On the left is the same model at the same discharge where the upstream boundary condition extent was across the channel and the full floodplain. Both configurations produce hydraulics at the bridge opening that are essentially the same, suggesting that either boundary condition is acceptable for hydraulic analysis. However, for sediment analysis, the difference in inlet conditions may produce different transport behavior, including differing calculated capacity supply loads. For this reason, it is important to ensure the upstream boundary condition extent is appropriate for the modeled flow. Additional care should be taken if a hydrograph is used that transitions between a low and high flow condition. Depending on the specifics of the modeled area and needs of the analysis, it may be appropriate to designate a channel input boundary and a floodplain boundary. The need for this additional level of complexity should be explored by investigating the sensitivity of the results in the area of interest to the configuration of the input boundaries. In addition to the width of the inlet boundary condition, the type of distribution selected can be important to consider as well. A conveyance-weighted inlet distribution is the default assignment in SMS and is frequently appropriate. The example model on the left was run at a very high discharge where the inlet boundary appropriately spans the entire floodplain. For this run, the inlet distribution type was conveyance. On the right is the same model at the same discharge where the inlet distribution type was velocity. Again, the hydraulics at the bridge crossing are essentially the same, but are significantly different at the inlet. In order to better determine the appropriate inlet distribution type, the hydraulic model was expanded further upstream. This provides a reference point for the flow behavior at the inlet of the sediment model boundary. Reviewing results for both the version of the model with the conveyance-weighted inlet distribution and the version with the constant velocity distribution reveals that the flow behavior at the location of the inlet to the sediment model boundary is the same for both models. This creates confidence that the hydraulics at the sediment model inlet are well characterized. Comparing the extended model hydraulics with the previous original results for the two distribution types reveals that at this discharge, the constant velocity distribution more closely matches the anticipated flow behavior at the inlet and reinforces the importance of evaluating the effect the inlet distribution type has on the results. In addition to the inlet distribution type, the upstream boundary arc is also where the modeler specifies how the input sediment load will be determined. The capacity option determines the sediment input based on the hydraulics and bed sediment at the upstream boundary. This is the simplest way to begin a sediment model and a common approach when the modeler has no information or insight into the actual sediment loading. The second option is to prescribe the sediment input load in an input file as either a time series or rating curve. This information is usually derived from a separate analysis of the area upstream of the model or from measured data. A time series input file specifies the volumetric flow rate of each sediment size class at discrete points in time. The format for the text file is hours in the first column, followed by the volumetric flow rate for each size fraction in subsequent columns. The flow rate is specified as either cubic feet of solid sediment per second or cubic meters. The size fractions correspond to the size fractions declared in the model control parameters that will be set up later. Comment lines are prefaced with double slash characters, and a minimum of 2 data lines are required. The model will interpolate the flow rate between each time step entry as needed, and will continue with the last time series entered at a constant value if the model execution period is longer than the time in the input file. The second type of sediment load input file is a rating curve. A rating curve describes how the volumetric flow rate of sediment changes over a range of discharges. A rating curve file is created by first placing rating curve on the first line of the file, followed by double slash lines for comments. The first column of numbers is the water flow rate, and subsequent columns are the volumetric flow rate of each size fraction. Choosing between time series or rating curve-based sediment input loads usually comes down to what additional information is available about the modeled system. Regardless of which method is used, evaluating the sensitivity of results to the sediment load is an important step in building a sediment model, and this topic will be discussed in more detail in a subsequent video. Sediment material zones are used to define how sediment is distributed through the model. Similar to roughness zones, sediment material zones are a configuration of connected polygons that cover the entire model extent with data obtained from field samples. Depending on how the roughness zones were delineated, it can be appropriate to begin by making a copy of the roughness zone coverage and changing the type to sediment material. Once this is done, double-clicking on a polygon will produce the window used to assign properties to the different sediment material zones. The left pane defines the different material zones. In this application, we will define one zone for a non-erodible floodplain. Selecting a useful color and texture will help ensure model areas are assigned the appropriate properties. A second zone is defined for the river channel. The right pane defines the different layers of sediment for each zone. These layers describe the vertical variation in sediment makeup within each zone, and each layer is assigned a thickness and gradation curve. When entering sediment gradation information, the units are always millimeters, and diameters are entered in order of increasing particle size. SRH2D recommends defining at least 2 layers for each sediment type. If detailed information is available about different layers in the zones, it should be entered. However, when no additional information is available, it is acceptable to use the same gradation from the first layer in the second. The thickness of each layer would come from sediment sampling, or in this case, when the sediment is assumed to be a constant gradation, it is appropriate to assign a shallow thickness to the first layer and a much greater thickness to the second. Be sure to select the appropriate units for the layer thickness. The total depth of layers should exceed the full amount of anticipated scour, because the model will not indicate that the full depth has been reached, and instead assume that beneath the last layer is a non-erodible boundary. Frequently in modeling applications, no sediment information about the floodplain is available. It is still possible to create a useful model because in most cases, the floodplain topography is relatively static and does not serve as a source of sediment for the rest of the model. In this case, it is appropriate to define the zone as non-erodible and to leave the layers as undefined. The model interprets these undefined layers as an area that cannot erode and is not a source of sediment. Sediment can deposit on a non-erodible zone, and sediment that is deposited during a model run can be eroded, but the element elevation will not go below the initial value. With the sediment zones defined, the modeler assigns the appropriate zone to each polygon in the sediment material coverage. In this case, the floodplain on each side of the channel is assigned type non-erodible, and the channel is assigned type channel. Non-erodible zones can be defined in the channel as well. Weirs or other permanent structures may be modeled as non-erodible areas, as is the case in this example. Natural features like a bedrock outcropping or in-channel island that in the modeler's judgment would not erode over the modeled time period can be modeled as non-erodible zones as well. If not already created for the existing hydraulic model, a monitor coverage should be created and populated with lines and points. Monitor lines and points are particularly useful in a sediment model because of the information they report during a model execution in the simulation run queue. Additionally, results reported for monitor lines and points contain information that complements the output values generated at each mesh element and can be useful in evaluating the success of a model run. If the coverage does not already exist, create the monitor coverage by selecting the type monitor under the SRH2D model options. Laying out a series of monitor lines across the model extent may be useful in detailed analysis about how sediment is eroded and deposited throughout the system. This example of a monitor line output file shows time series results for a number of parameters. In addition to the discharge and averaged water surface elevation found in hydraulic models, sediment results include the sediment transport rate across the line, average sediment concentration, minimum bed elevation, and volumetric flow rate for each size fraction. Similarly, monitor points report the sediment gradation profile on the surface at the point location. Placing a monitor point at a key location, such as an area of expected degradation, will reveal how the surface gradation changes through the model run and may be helpful in understanding the nature of the bed change. This concludes the second video in this series on sediment transport modeling with SRH2D, which covers recommendations for converting an existing hydraulic model to a sediment transport model. In this video, we discussed the model extent and considerations for adjusting the mesh to ensure the element size, total number, and density are appropriate. The location of upstream and downstream boundary conditions, inlet distribution types, and sediment supply type were also covered, as well as the creation and assignment of sediment material zones and the value of using monitor lines and points. In the next video, we will discuss the parameters specific to sediment modeling. For more information on additional videos, documents, and other reference material about two-dimensional modeling and SMS, please navigate to the link provided here.